Hello, my name is Miao-Xu Peng. I'm a PhD candidate at Peking University. Today, I want to introduce our work titled by Heterogeneity-Aware Distributed Machine Learning Training via Partial Reduce. The success of modern machine learning lies the foundation of increasing amounts of data, emerging elaborate machine learning models, and the development of computing infrastructure. With the increasing size of data, training the ML models on a massive data is becoming more and more time-consuming. The target of machine learning is to find a model that minimizes the empirical risk on the datasets. Most of the existing systems rely on a data parallel computation schema and follows a distributed mini-batch SGD algorithm, where the model is trained over different parts of the dataset. The model parameters are synchronized at the end of each iteration. The synchronization operation guarantees that the distributed training paradigm can achieve the same convergence property as the sequential training counterpart. The existing methods typically assume a homogeneous environment. There is no significant struggler in the computing nodes that might block the others. However, the homogeneous assumption is not always available in reality. Heterogeneous environments are very common in real-world applications. For example, due to the massive amounts of data, many large companies such as Google, Microsoft, and Tencent choose to store them on tens of geo-distributed data centers. The communication within a data center could be 10 times faster than between data centers. Even in the same data center, heterogeneity still exists because of different network interface cards, network PCIe switches, and a hierarchical network topology. Deep learning is a compute-intensive and hence heavily relies on powerful but expensive accelerators such as GPU. Since these accelerators are developing quickly, different generations of hardware could have quite distinct computation power. Collaborative training with heterogeneous clusters is much more cost-effective than replacing all outdated devices. The third case comes from resource sharing. A common practice in large companies nowadays is to utilize cluster schedulers, such as Kubernetes, to manage clusters of tens of thousands of CPU and GPU resources. The jobs could differ from the others in terms of memory usage, CPU and GPU core utilization, network bandwidth, and so on. To improve the cluster utilization, multiple containers could be placed on the same physical node or even the same physical GPU by virtualization. As a result, the containers of the same job could perform distinct hardware efficiency due to resource sharing. Existing distributed ML systems mainly use two communication architectures. The primary server stores a global model in the central node, and each worker fetches the model from the parameter server, computes a mini batch of stochastic gradients, and pushes them to the PS to update the global model under certain consistency protocol. Another line of approach is the decentralized training. For example, our Reduce uses high-performance communication techniques for model synchronization, such as ring reduce, assuming the workers are connected with a ring network. For heterogeneous environment, suppose the red color represents for the effects from the struggler. As we can see, our reduce is fundamentally synchronized and all the workers are blocked by the struggler. For the parameter server architecture, this architecture matches the requirements of asynchronous communication, where each worker calculates its gradients and updates the shared model without waiting for the strugglers. However, they cannot benefit from inter-GPU communication channels when deep learning models are evolving over GPUs. Therefore, we are trying to answer the following question in this paper. Can we elevate the efficiency degradation in the heterogeneous environment over the all-reduced architecture while maintaining the best possible convergence performance? In this paper, we propose partial reduce, where each worker only needs to synchronize among p random workers without waiting or blocking any other workers in the current iteration. Here is our system overview. The controller is responsible for managing the partial reduce operation among the workers. Here is the detailed partial reduce algorithm. Now we give a running example to illustrate the difference between our reduce and our method. Suppose there are 8 heterogeneous workers running a DL job. Near a certain clock, the workers 1, 4, 6, and 7 just finished the forward and backward computation. Later, worker 2 and 3 also finished the job. At this moment, the above 6 workers are blocked by worker 0 and 5. However, in partial reduce, we suppose p equals 3. When worker 1, 4, 6 finish the computation, this should send a ready signal to the controller. Once the controller finds there are enough workers, it will send the group information to the workers. Then the worker group performs a partial reduce to exchange their model information. In heterogeneous environment, partial reduce elevates the idle time on synchronization and improves the resource utilization. We describe the partial reduce algorithm as follows. Then we provide a theoretical convergence guarantee of our partial reduce algorithm. The theorem shows that the convergence bound can be decomposed into 2 parts. The first 2 atoms come from the distributed SGD training, which is similar to that of the vanilla SGD. When we increase P, the upper bound could become more substantial and suggest us to give more iterations for convergence. The last term is the network error, resulted from the model difference among the workers during training. We also find that more heterogeneous the environment is, the smaller spectral gap and the larger network error bound we have. We improve the constant partial reduce algorithm by penalizing the stale model parameters during the model aggregation step. We first describe an abstract example to illustrate the staleness during our partial reduce. Suppose different workers start from the same model initialization. The slow workers might meet the other fast workers after different iterations. As shown in this figure, we assume p equals 2 and worker j is 3 times slower than worker I. When worker j finishes the first iteration, worker I is already very close to the optimal point. However, xi has to be averaged with the delayed model xj in content partial reduce, which leads to a model degradation on worker I. Therefore, it is still worthy to study the model aggregation route to prevent the impacts from the staleness. Inspired by the exponential moving average technique, we assign the smaller weights on the models with larger staleness. We compared partial reduce with 7 baselines, including R-reduce, eager-reduce, ADPSGD, PSBSP, PSASP, heterogeneous PS, and PS backup workers. Our experiments show that partial reduce is up to 2 times faster than our reduce. We further analyze the hyperparameter P in our partial reduce. The per update time is positively correlated with P, and the number of updates performs conversely. Therefore, the total runtime is the product of them and might have 2 possible minimum values. For 16 workers, partial reduce is 16.6 faster than our reduce in per update time and achieves 2 times speed up in total runtime. Our partial reduce also achieves high heterogeneity tolerance and improved the scalability with flexible parallel asynchronous p-reduce operations. We summarize our contributions as follows. We target the disadvantages of the R-reduced training method in heterogeneous environments and propose a novel partial reduce algorithm for efficient distributed training. We theoretically analyze the convergence property of partial reduce and obtain a convergence rate. We capture the stillness in the training process and propose constant dynamic partial reduce mechanisms for better convergence performance. Experiments on a production heterogeneous cluster demonstrate that the significant efficiency improvement of our methods on different workloads. Thanks for listening.